Hi, Jeff here with the Nurture Nature Center, and today I want to talk to you about sound. Now, sound can be annoying and distracting, it can be useful and convey information, and it can be beautiful and entertaining. But what is sound? Sound is produced by vibrations, and these vibrations can travel through stone, metal, air, or water. The vibrations that travel through air or water interact with our ears, and we sense these vibrations as sound. Notice that sound can travel through as objects as different as metal and air, but it has to travel through something. Sound is a vibration in a medium. Sound cannot travel through a vacuum. To better understand how sound waves travel through the air, we can look at how waves travel through other objects. Sound waves act very similar to the waves that I can generate with this slinky. So for example, if I just wiggle the slinky, you can see a wave passing down the slinky, and it actually reflects at the end of the slinky and comes back to me. For sound waves, when we have a reflected sound wave, we call this an echo. We can use our slinky to look at other properties of sound too. So for example, the loudness of a sound, the volume of a sound, that's a measure of the amplitude or the difference between the wave crests and the wave troughs of our sound wave, or indeed with our slinky wave. So a quieter sound wave would look more like this, and a louder one would look more like this. The amplitude was much greater for that second wave that I produced. Sound also has frequency. A low-frequency sound wave is one where the distance between the wave crests is larger. And a high-frequency sound is one where the distance between the wave crests is much shorter. And I can produce a higher frequency simply by wiggling the slinky faster. If I wiggle the slinky at just the right speed, I can actually time it so that the waves I'm producing at this end match with the waves that are being reflected at the other end. And I can cause resonance. The waves become much stronger at that point, and they also appear to freeze. They appear as if they're not moving anymore. These are standing waves, and I can create them with sound or with this slinky. In a large, relatively empty room like this one, echoes can be a bit annoying. They can make it hard for an audience to hear the speaker, which is why in this room we actually added acoustic panels to the ceiling. There are these black squares all over the ceiling, and these just act to absorb sound waves. So in the Nurture Nature Center, in this sphere room, we're trying to suppress echoes and sound waves. But sometimes you try to amplify them, sometimes you try to concentrate them. The human ear is specially shaped to concentrate sound waves into the inner ear, where we can sense the sound. And you can also make a bench that can do this. This is called a whispering bench. It is specially shaped to concentrate and amplify sound. Now in the distance there, you can see a small green object. That's a battery that's powering a small speaker that's producing a tone, a sound right now. You can't hear it on camera. But if I just get a little bit closer to the whispering bench, suddenly you can hear that tone very clearly. And now let's move away again. The sound is still playing, but you won't hear it anymore once we move away from the whispering bench. Now, the sounds that we can hear come in a range of frequencies, and using this online tone generator, we can generate different frequencies and see how they sound. So in addition to the tone generator, I also have an oscilloscope app on my cell phone, which is showing us the frequency of the sound that it's hearing. I'm going to play a pure tone at 293 hertz, and watch what the oscilloscope does. So you can see that the waves are closer together. There are more waves. Now, human hearing is remarkably sensitive, and we can hear frequencies over a very wide range, but not an infinite range. Below about 20 hertz, people just can't hear that kind of vibration in the air. That's called infrasound, anything below 20 hertz. And some animals can hear infrasound. For example, elephants can hear much lower sound frequencies than humans can. And there's an upper limit to how high of a frequency we can hear. The upper limit of human hearing is about 20,000 hertz. That's 20,000 oscillations per second. That's a very high frequency. And in fact, I'm going to play a 20,000 hertz sound right now. I can't hear it. If you look very closely at my oscilloscope, you can see a whole bunch of waves packed together. If I was generating sounds above 20,000 hertz, and I can't generate sounds that high with this tone generator, but if there was a sound higher than that in this room, I wouldn't be able to hear it. Well, bats can hear sounds well above 20,000 hertz, and we call this ultrasound. If sound can only travel at 770 miles per hour, what if an object is moving faster than that through the air? Well, that's how you create a sonic boom. A whip cracking is actually producing a loud snap because the tip of the whip is moving faster than the speed of sound. So when you hear a whip cracking, that is a sonic boom. When you hear thunder, you're also hearing a sonic boom. A lightning bolt is so hot that the air around a lightning bolt expands away from the pulse of electricity faster than the speed of sound, creating a sonic boom. And also, when you see a flash of lightning, the light from the lightning reaches your eyes almost instantaneously. Light is incredibly fast. Sound is much slower. So what you can do is you can actually count the amount of time it takes for you to hear the thunder after you've seen the flash of lightning, and you can use that to determine how far away the lightning bolt was. So we've seen how sound waves behave with slinkies. We've observed how they can echo and bounce, and we even saw them on an oscilloscope. But with a device called a Rubens Tube, we can actually see sound waves. And this is a Rubens Tube that I've constructed right here. So it's a long tube, a 3-foot long tube, that has perforations in the top that allow gas to come out. So we're seeing a flame here. Now if I pass a sound wave through here, which I can easily do because there is a speaker connected at that end, the sound wave travels down the tube and it bounces off of the end of the tube and then it goes back. And if we send a sound wave down this tube that resonates, that causes echoes that amplify the original sound wave, then we can actually create standing waves, just like the ones that we saw with the slinky. And those standing waves push out the gas more in some places and less in other places, and that allows us to actually see the sound wave. So I'm now playing a 450 hertz sound wave, and you can see peaks and valleys in the flame behind me. The peaks are the wave crests, the valleys are the wave troughs. If I change the sound frequency coming out of the tube, then we can change the shape of those peaks and troughs. Using the Rubens Tube, we can even see music. So here I now have playing Für Elise, and as the different notes play on the Rubens Tube, you can see different patterns emerging, different sound waves producing different wave crests and wave troughs. It's all very beautiful. You can easily create a tool that allows you to see sound as well. All you need for this is a large bowl and some cellophane and some salt. Take the cellophane and stretch it over your bowl, nice and tight, make it a nice airtight seal, and sprinkle some salt on top of the bowl. This now acts like a diaphragm, and if it's exposed to a loud enough sound, the cellophane will vibrate, and you should see that when the salt begins to vibrate. Let's see if I can make a sound loud enough to make the salt vibrate by hitting this pot. Well, that was a fun experiment that I certainly encourage you to try at home. Just make sure that if you're going to try this, to not make a lot of noise at inconvenient hours, because noise pollution is a really serious problem. It can lead to stress, which can contribute to cardiovascular disease in people, and it's harmful to animals too. It affects their behavior. Catch you next time. Thanks for joining me.